Hi, I'll be talking about Raspberry Pis and circuits, but before I start, I just wanted to point out that we'll be talking about circuits, and circuits have electricity. And unfortunately, electricity is also an invisible hazard. So I want to point out a few good practices that you and your student or whoever you're mentoring, like the case was for me, to practice so that you're safe and also not going to damage your hardware as well. So remember to turn off your Raspberry Pi every time you make modifications to your circuit. Make sure there's no food or drink near the workspace. Work indoors in a dry location. Don't work on a conductive surface such as a metal table. And if you've never built electrical circuits before, be sure to follow the instruction manuals very carefully, heed the warnings, and be aware of some learning kits like snap circuits, which are great about teaching how circuits work and also the hidden dangers and how you can protect yourself and make sure that you don't damage the projects or the equipment either. With that, I'm going to start the presentation mixing a Raspberry Pi with Python into a 5th grade science fair project. My name's Wendy. I have a background in electrical engineering, and I also want to thank the PyCon committee for choosing this talk. I had a lot of fun doing the project and really happy to share it with all of you. And in fact, the photograph that's in the center here is from a summer science fair, science fest actually, that we have in our town, and this is the Crazy Science booth. At this booth they had these wooden tracks of different shapes, and kids could go in and play with billiard balls and see which ones would be slow or fast and compare them with the different tracks. My son was very excited about that project, but he wanted to take it to the next level, and so for his 5th grade science fair project, he wanted to actually measure the speed of each ball going down a track. And because we had done some work with Raspberry Pis a couple summers ago, he wanted to use a Raspberry Pi to make those measurements. So today's talk is basically some project tips to lead you on a successful project, whether it's your own or if you're helping another person like I was. We'll summarize how to get started with the Raspberry Pi while using the GPIO with circuits and the hardware. GPIO in this case stands for General Purpose Input-Output, and those are the pins that we'll be talking about that we hook the Raspberry Pi into external circuits. We'll also talk about some interesting difficulties that we had during the project and share those with you. So some project tips. First of all, critical warning, big news here. Raspberry Pis can be super addictive. So in my case, I had to practice a lot of self-restraint and restrict myself to only provide help when the student asks for help. A warning for you all, it's easy to let the project grow to this gigantic size that you can't finish in the time allotted, so feel free to steer your student. If you think the project's getting too big, you can always promise to add more things to the project later if you finish early. Some information for you: seek help from your local college professors or a local makers group with your student if you need advice on, say, tools or sensors. Don't worry about not knowing the answer to everything. We can't be expected to know everything, and it's also good. You might learn something new from speaking to these people. Another piece of information is it's a good idea to take a project and not try to finish it all in one afternoon or one day. It worked really well where we actually set up aside a couple hours a weekend for several weekends in a row to work on the project. It helps break up the project, reduces stress and anxiety of trying to get it done by a certain time. Debugging. Every project needs to be debugged. Something's not going to work, something's going to break. And when you're just not making any progress and you see the frustration levels going up, feel free at that point to go take a walk, or even better yet, just sleep on it. Also, take pictures and videos throughout the project. That's useful. And finally, try to stay as positive as possible. Focus on the things that work. And whenever you're stuck on a project or a problem that you can't solve, it's really easy to start looking at the things that do work and narrowing it down so that you can find that one or maybe two things that are not working and solve that problem. And apply that to any of the projects, whether or not it's your own or you're helping somebody else. So the background of the project, my husband and my son went to a hardware store and they bought some material to make tracks. And it turns out it's in the picture there, you're seeing the two tracks they built. It's out of this material that you normally would use to hang, say, shelves on a wall. And they bent one and kept one the same. And also, you can't tell quite in the picture, but the top and the bottom of each of them are the same height. So the question we had was, now that you've got this set of tracks and we want to measure speed, how do you do that? I wasn't really sure how to do that. I didn't have any background in it myself. So we ended up talking to a ex-college professor that we knew who's taught Physics 101, and his recommendation was use a Photogate. So what is a Photogate? The blue shape that you see in the drawing here is a Photogate. It has two parts to it. The left side of this particular drawing is your light source. So the light source could be an LED, a light emitting diode, or it could be a laser. And then on the other side you have a phototransistor, and a phototransistor will basically detect whether or not it can see that light or is something in the gate that's blocking that light. Now, a phototransistor is essentially a special type of transistor, and it's a switch. And the beautiful thing about this switch is that when you shine light on it, the switch allows current to flow, and if you don't shine light on it, the switch is open and no current can flow through it. And so it's the same type of switch like you would use as a switch in a room to turn on a light. Same type of concept. And what's really cool about this is that when it sees light, the voltage will be low, and when it doesn't see light, the voltage will be high. And the circuit to the right is a diagram for those of you who are familiar with circuits. And for those of you who are not familiar with circuits, just understand that when the beam is blocked, you'll see a low voltage, and when the beam is blocked, you will see a high voltage. And when we get to the Raspberry Pi part, low voltages are equivalent to 0 and high voltages are equivalent to the number 1. And we'll talk a little bit more about that later. Now that we knew that we were going to use a Photogate, we decided to get on to Google and look at YouTube and see if anybody had actually built a Photogate for the Raspberry Pi, because we didn't really know how to get started. Well, it turns out the link that I show here from YouTube is a really nice video that's done on how to get started with a Photogate using the Raspberry Pi, and so it was the basis of what we used to put this project together. Okay, so getting started with the Raspberry Pi, how do you get started? What's the right order to do things? So for those who have never used a Raspberry Pi before, I would direct you to the raspberrypi.org website, and they have a bunch of vendors listed that have all sorts of different kits with different parts that you can get. So CanaKit was an excellent kit. I'll be talking about that in a little bit. And then also be aware that there are several Raspberry Pi versions. Version 4 just came out recently. Version 3 is what we used for our kit, and it's older. And also, the kits often come with a micro SD card with Noobs. Noobs stands for New Out-of-the-Box Software, but essentially it's a Debian Linux operating system. You plug into the Raspberry Pi, and when you boot it up like you would any other computer, it boots up with a graphical user interface, such as, Macs or Windows or any other type of flavor of Linux that you might run. It's the same sort of thing, and it's really nice. You can get in there, it logs you in, and you can play with it. They've got a lot of pre-installed software. Python's already on there, and there's even some IDEs to play around with Python software. So it's really kind of a ready-to-go kit that helps you get going, and so that's why I recommend a kit is a really good way to go if you've never used them before. If you don't get the kit, be sure though to get the micro SD card, unless you like installing operating systems on or downloading the code and putting it on a micro SD card. The last thing I would also recommend is that if you're familiar with using virtual environments, definitely use them. If you're not that familiar with virtual environments, there are a lot of online resources that you can basically Google virtual environment and there'll be descriptions of how to set them up. And they're a really nice way so that each project that you have will have a different set of installed dependencies from the Python package manager. And so it's just a good way of doing it. Now, before I flip to the next slide, I just want to point out in this photograph at the very top of the Raspberry Pi picture, you'll see a row of pins sticking out of it. That is your GPIO connector. So to get hooked over to your circuits, you need some way to access those pins in a very handy and useful manner. And so that's where we move on to getting a kit for doing that. And the kit I recommend is Freenovi's Ultimate Starter Kit. It's a $50 kit from Amazon. And what I liked about it is that they provide the ribbon cable, which is that gray cable that's coming over to this breakout board. They provide the breakout board with the labeling for all the different GPIO pins. And you can take that and plug that into a solderless breadboard, and that's what you see in that upper right picture. The middle picture also shows sort of a perspective view where you can see the Raspberry Pi connected via the ribbon cable over to a solderless breadboard. So that kind of gives you an idea of how it all gets connected together. Now, what I also like about Freenovi's kit is that it's got some LEDs and some motors and displays and number pads. They have a GitHub repository and then a PDF tutorial. And the tutorial walks you through every single device. So the first tutorial is take an LED, grab a resistor, and that's going to be your current limiting resistor, and it shows you exactly how to wire it up to this breakout board. And then they have sample code that immediately once you get it running, will blink the LED. And it's like your own hello world for circuit hardware to get that LED blinking. And so it's really nice kit. It's a really nice PDF tutorial, and I like how they go into great detail if you've never done it before. Now, one little gotcha that I wanted to point out is it may not be totally obvious how to plug the ribbon cable from the GPIO header over to the board and not get that messed up. So a little trick that you can do is you can take your Raspberry Pi and flip it over, and that's what the bottom right hand picture is that you're looking at the back side of those pins, the dual rows of pins. All the pins will be circles, but one will be a square, and that square is your pin number 1. Now, ribbon cables also will have one side that's painted red. So what you want to do is make sure that the red side is on the same side that that square pin is once you flip the board back over. And then just be really careful when you plug the connector into the row of pins. Make sure you're not offset. You want to match every single pin for every single hole in that connector. And that's the only drawback of using those types of connectors, is they're not keyed in any way to prevent you from plugging it in wrong. You can plug it in wrong. So just take extra care when you do that. The next thing I wanted to go over is some recommended tools. Get a breadboard wiring kit, and the picture to the far right is a picture of one of those kits. It's really handy. It's a bunch of colored wires, different lengths, and they're already pre-stripped for you, and they fit perfectly into the holes of the solderless breadboard. And because they're all different lengths, you can find the right length to go between what items you're trying to connect in your solderless breadboard. And they're just super handy to have, especially the fact that they're pre-stripped. Another type of wire you can get are these wires that have the big black heads that you can plug into the different holes in the solderless breadboard. And then another type of wire that's cool is on one side you plug it into the solderless breadboard, and then there's a nice alligator clip on the other side if you need to attach to something external to the solderless breadboard. These types of wires are easily found at places like SparkFun or Adafruit or even Amazon. So feel free and take a look at the different items you can get to help you build up your circuits quicker. The next thing I wanted to suggest is getting a good multimeter. This is a Fluke 179 that I use. I bought it so that I have one meter that I use forever, and it's a great, robust multimeter that should last you a lifetime. Now, I understand it could be out of your price range, and that's understandable. So if you're going to buy some El Cheapo multimeters, if you can, buy two of them, and that way if one's reading weird, you can use the other just to double check that it's working right. I've helped numerous people with multimeters where one wasn't working and they were going crazy because they couldn't figure out what was going on, and it was the meter. The last thing I'm going to point out is the bottom left picture is a picture of a perforated board. So when you're using a solderless breadboard and putting up some sample circuit, the idea is that when you're done, you just pull the components off of them and you're done. But you might want to save it. So if you want to be able to save a circuit that you've built, you can use perfboard. Now you'll have to learn a skill called soldering to be able to solder your items onto there and make a perfect, not a perfect, but a permanent board. And that's wonderful to do. But you'll have to learn the soldering skill, so just so you're aware. So I've talked about solderless breadboards. Well, how do you use one? So on your GPIO cable or breakout board that's going to come over and plug into the breadboard, there's going to be two things you're going to need to wire in. You're going to need to wire in your voltage rail, and you're going to need to wire in your ground rail. And the voltage, there's actually two voltages produced by a Raspberry Pi. There's a 5-volt one and there's a 3.3 volt one. And the 5-volt could go, say, in that top row that you see here, and then you could put maybe the 3.3 volt rail in the bottom one there. And the red lines that I've drawn on the solderless breadboard, they're supposed to show how the pins are connected. So once you plug 3.3 volt into, say, that red line there, every hole that's along horizontally will all see that 3.3 volts. The ground is also the low potential reference point for your circuit, and that needs to be the same between your circuit and also your Raspberry Pi, and so that also needs to be plugged in. So you'll want to take the pin that says GND on your breakout board and plug that into one of those black rows. It could be the top one or the bottom one or both if you prefer. Just know how you've wired it up. Now the center of the solderless breadboard's wired differently. The pins are wired vertically, and those little short red lines going up and down shows you how they're connected together. Now we didn't use these for our project, but they are very common. So I took a picture, or I grabbed a picture from Wikipedia of a dual inline package part. So if you use timers or AND gates or OR gates, they'll be packaged in this type of part. When you get one, you can see the pins sticking out of them. They actually are designed to go straight into your breadboard. So you would just shove that straight down, plug it in, and now through the pins that are sticking out from, or the holes sticking out from the pin that they're plugged into, now you have access to all the pins on that part. And now you have the ability to wire up that circuit. So those are just a few tips. You want to try to keep your wiring as clean as possible and try to be as neat as you can, because it makes it easier to debug your circuit. And the last tip I wanted to throw out is that after you're done breadboarding your circuit, one thing I like to do is I like to take my multimeter, I like to put it in the resistance mode or the ohm mode, and plug my black probe into either of the ground rails, and then plug my red probe into both, if I'm using both, the 5-volt rail and the 3.3 volt rail, and check that I'm not reading 0 ohms between them. If you're reading 0 or 1 or 2 ohms, that means that somewhere in your circuit you've managed to almost or just about wire or short your voltage rail to your ground rail. And that means that when you turn on your circuit, you're going to get a big puff of smoke or damaged parts or carbon across your circuit, and maybe even damage your Raspberry Pi. So it's a good thing to check that out just before you get started. Now, we've talked about the hardware. It's time to go to software. So we have Python 2 and Python 3 available on all the two Raspberry Pis I looked at. So like I said before, we used a Raspberry Pi Model 3, and we did it with Python 2, not realizing that was important now that Python 2 has been, the support for it has ended as of January 1st. But what we did to install is the first lines there, the git clone, the build, and then there's GPIO-V, which is a command that checks to make sure that your GPIO has been installed. And then we did finally one last pip install of the RPI.GPIO package. That is what we needed to do. Now it looks like you can kind of replace that with pip install wiring. But what I found even cooler than that was that after I heard about the Raspberry Pi 4, I thought, well, let's try this Cana kit. And I really like the Cana kit. It's really good for someone who's never used it. But the other thing I really liked about it is if you type Python at the command line on the Cana kit, it already comes with 2716. And then if you type Python 3 at the command line, it's got installed 373. And then pip, which is the package installer, if you use pip without the 3, it's telling you which packages have been installed for 2. And if you use pip 3, which was, they were both there, they both list RPI GPIO version 065 already installed. So you didn't have to install any software. It just worked right out of the box. So that was really cool. And then just be aware that you can also clone the software from GitHub for free Novi. And it's the free Novi Ultimate Starter Kit, and that's where you get the Python code for all of the different devices such as the LEDs or motors and all the things that you can play with in their kit. Now I want to talk a little bit about how to use a diode. Why? Well, we had to use some LEDs for our circuit. And just be aware that a diode's job is to allow current to only flow in one direction. In this case, it goes from the anode to the cathode. A cool trick you can learn using your multimeter is if you grab an LED and you have no idea what direction it's supposed to be, which is usually the case, at least for me, maybe there's a good way to look at it, but my eyes aren't that good. But what you want to do is take the red probe of your multimeter, put the black probe, so the red probe is going to go on one leg of the LED and then the black is going to go on the other leg. Put your multimeter into diode mode, and if it's set up correctly, it will light up. If it doesn't light up, just switch the probes, and now you've figured out the direction of your LED. Now I'm going to go ahead and run a little video here while I talk about the IR diode that we needed for this project. So IR stands for infrared, and here we have a little item where we've got a IR LED wired up, and the question is how do we see it? Infrared is not in the human visible range. So we were able to plug it in and then take it off, and you could see that there's a little tiny light there. That little tiny light is the IR LED shining, and the way we were able to figure out that it was on is we tried a couple of cell phones in our house, and it turned out our newest cell phone could see in the infrared region. So you put it in camera mode, and then we were able to shoot this little video. Now, note how dim that light looks, because that's going to feed into the next slide I'm going to talk about. And one last thing is when you are playing with LEDs, don't forget your current limiting resistor. If you plug an LED straight on a power source, such as a battery, you're just going to drain all the current out of it in no time, and you might actually burn your hand while you're holding it or burn up the LED. So just be aware that you need to always have a current limiting resistor when you're playing with diodes. So that little tiny IR diode wasn't bright enough to see, and it turned out once we put it on a gate, it always showed that the light was blocked. It never could see any light. So what we did is we went ahead and just replaced the IR LED with these little finger flashlights that the photo transistor was able to detect. So the red box there just shows that little battery that we used. The green box shows what our phototransistor circuit looks like, and that's the receiving end of the Photogate. I've also got a little picture of a little tiny phototransistor there. I mean, we're talking millimeters by millimeters little part to see it, but essentially all we do is wire that up and wire there's two, so we needed a start gate and a stop gate to be able to measure when the marbles left the beginning of the track and then when they got to the end of the track. So that's why there's two of them. And each of those is wired into GPIO address line 17 and 18 is what we used for this kit. And then the blue box shows what I call my sanity circuit, and that was wired up to just one of the gates, or one of the photo gates, where we would basically put our hand in between the phototransistor and the light source and just see if that LED flashes on and off. And as it flashes on and off, you could say whether or not that circuit was working. So it was a good check. The other quick thing I wanted to mention is that I didn't have a circuit drawing or a schematic drawing program at home. So I went to circuit-diagram.org, or I found that online, and I was thrilled that they even had a Raspberry Pi breakout board. So if you want to draw your own circuits, feel free to go to this website and draw your own circuits and build them all up. It's really nice. That was a nice feature. Now, GPIO inputs can be challenging because outputs are easier because you can basically blink the LED and go, yep, it's working, or nope, it's not, maybe I got to go check the address. But inputs, how do you know they're working? So first of all, you want to find your addressing. So CanaKit, again, I really liked because they have this nice color printout of the GPIO pins, and they're colored, and it tells you what address is which pin. Super handy. You can also, at least on the older Raspberry Pis, use the GPIO read all command, and that will print out an ASCII display of the entire pinout of and the addresses for those pins. So just be aware you could use that. And the next thing that we did is we actually wrote a little tiny piece of code, and all this code does is it just sits there and checks a particular address and sees if you can see changes on it. So what we do is we import sys and the RPI GPIO package. Then we set up the GPIO, which is simply GPIO set mode for GPIO board. And then you want to make sure that you've picked an address that you're interested in, and then use GPIO in to set that it's going to be an input pin. And then the try loop just continues and reads that pin. So if there's changes, you should see them. So in our case, we plugged in, picked an input for one of the phototransistors on the receiving side of the Photogate, kept that running, and we looked to see if we would see 1 or 0, 1 or 0, and sure enough, if it was wired correctly and you had the addresses correct, you could see that change. And so this is a nice, useful piece of test code to check that out. Now I'm going to let this run. This is the experiment in slow motion. We have a gate that releases the two marbles, and they are fortunately far enough apart that we can write the code the way we did. And this kind of shows you where the start gate is and where the end gate is, and the little photo in the bottom right is a picture of on perf board the circuit to build up the little photo transistor there, and that little tiny square is the photo transistor that we used. Okay, so now we just need to modify that input code so that we can take care of all the different states. So the states that we have a start state, we have the first marble has arrived state, then we have a wait state because we want to wait until that first marble leaves the end gate, and then make a timing for when the second marble arrives at the second gate. And just be aware that while this thing is running, that there's probably on the order of maybe 1,000 reads per second. So you want to make sure that you wait long enough before you try to measure the second marble, because it's basically going to stay high for a while that marble is traveling through that gate. Now, if that doesn't make any sense to you, another way to think about it is using a time chart. So in this case, 1 equals the gate is blocked, and 0 means a gate is open. And what I have is 2 columns showing in time the start gate on the left side and the end gate on the right side. So when the marbles are sitting up at the start gate, the gate is blocked, and so you see a 1. And what we're waiting for is when they both leave, then we start the timer, because we see that there's a 0 there, the timer is started, and we're going to wait. Now we're waiting for the first ball to arrive, the end gate. When that happens, we can record the first time. Then we need to sit there and read and read and read until that first marble has cleared that gate. And once it's left the gate, then we can say, okay, now we're waiting for the next marble. And when the next marble comes in, we can record the second time. And now this is the code that basically sets that up. Now I know there's a lot on one slide, so if you don't want to stare at this slide, I've also provided a GitHub site where I've stuck the source code for also that input test code, and then this code as well that you're welcome to take a look at. But in just sort of a high-level overview, everything on the left side is getting everything set up, and then the very bottom where it says initialize gate change state, those are just a bunch of flags that help you figure out what state we are in. Are we waiting for the first are we waiting for the marbles to leave the first gate? Has the first marble come? Is the second marble done? And are we done? So those get all set up, and then the right-hand side is basically a while true loop that runs continuously, and it's just polling where we are in those different states. So when it sees the state that, hey, we're at the first marble, go ahead and time it. When it sees that it's got the first marble, but the first marble's still there, it's just sitting there waiting and waiting and waiting and waiting until it leaves. And then it's ready to measure for the second marble. And then when everything's done, it records the 2 times. So when this code runs, what you're going to see is essentially a start time and a stop time, a start time and 2 stop times for each of the marbles, and then the calculated travel time of each marble. And so that's what my son used for his project. He did time trials, so he did, I think, 10 of them per marble, or I should say he did 10 executions down the track. And then he took that data, and he likes Jupyter Notebook, so he put the data in Jupyter Notebook and did a plot of the different runs and how the timing came out for each of those runs. So that was his science fair project, and he was super excited to do it and seemed to have a lot of fun with it and enjoyed playing around with the data. To conclude, just want to remind you, be safe with electricity again. Take small steps when you're putting your project together. I think that's what helped us out a lot. Define addresses before you get started so that you kind of have an idea of where you're going, and you know that whatever pin you're using is going to be mapped to whatever address you've picked, and just if it doesn't work, there's test code to try things out. Use small test codes and small pieces of hardware to check out stuff and build up your project. I think that helps too. And in this case, we use states with flags to define the measurement points, but maybe there's another way that can be done. And finally, the last slide here is we have some references and useful links on this page. Just a quick picture, my son ended up getting to go to district science fair, which was super cool, and he placed 3rd, so we were really proud of him. And the references and links that are here are all that were listed in the slides. And then finally at the bottom, if you have any questions and want to contact me, feel free to contact me through LinkedIn. I'd be happy to answer any questions, or if you have any comments, I'd love to hear from them. Thank you for attending this talk, and hope you have a great day.